Okay, so the electric field has been, well, always, it's been quite an interesting topic. It arises as a vector field, but we understand it through the idea of a force equation that is Coulomb's law. So, we wanted to ask a question: what does it look like and what is its behavior? How can we quantify it? How can we measure it? This is where ultimately we're able to arise with the idea of electrical flux and Gauss's law, and especially the interactions in between the two, the relationship. So, let's start with an idea. We have a charge. This is our charge. He's alone, no one's acting on him, no one's changing it, no one's doing anything to it. We have this surface. This charge has its electric field. It comes at an angle. It goes through our surface. What if we said, let's take a dot product between this surface? Well, what we immediately recognize is that they come out directly normal to the surface. As far as we're concerned, this is good. This means it's coming straight at it. There's no angle to it. It's not parallel to it. If it was a particle right there, it would be making a good even force. So, let's suppose we had a surface around the entire thing. We're going to make an argument based off of that later, but I do want to get that thought started. What happens if we enclose a charge? Now, back to this. This is flux. We decided to measure that dot product between an electric field and the surface that it is going through is going to be the electrical flux through that surface. It's often going to be denoted using phi. So there it is. Just to get you comfortable with it, phi e. Sometimes you'll see a boldface E, sometimes you'll see it like that. Mine kind of look like epsilons. That's just how I do it. So, do it whichever way you're told to do it or like to do it. Whatever keeps you out of trouble. Now, the formalization of what we just said is going to be through a surface. That's what a double line integral represents. Through a surface, the electric field dot product with, well, the normal vector, unit normal, to that surface. There. We have this. Gauss's law says to us that it is the charge enclosed. Okay, well, we're going to have to make an argument on that, but that's okay. Let's instead also look in the other direction. We know that it is going to be equal to the volume integral of that divergence, or you'll also just see it as shown in the Maxwell equations as just the divergence. Don't worry about divergence if you're not familiar with it. All it means is the stuff coming out of it. Basically, it's like a hose that's shooting water out. Is it taking it in? That would be negative. Shooting it out is positive. It's like producing something from a point. So that's our inherent statement. This is inherently for flux itself. This is for the flux coming from a charge through a surface that is containing it. But let's go ahead and try to make the argument for it. There, we have our sphere. And I'm sorry I'm not so great at presenting right now. It's been a while since I made a video, so I'm still kind of getting that little groove. So yeah. Here's our sphere. The surface is inherently that double line integral that we were seeing. So let's write it out. Our flux is going to be equal to double line integral through that surface of the electric field, which in this case, we don't want to do it based on x, y, and z. So we're just going to do it in terms of radius, angle 1, angle 2. Okay? Then dot product with the normal of our surface. Okay. So let's try to make this nicer, because I don't know what from our origin it would be if we were to have multiple particles with all of these. So fortunately, because we decided this is how we were going to construct it, we have a uniform radius across all of these. At this point, by the definition of a sphere, it's the same distance as this one, this one, this one, this one from the center. So, okay, we took one out of it. Okay, now let's think about it. What does angle have to do with our distance? Nothing. It has absolutely nothing to do with our distance. So we just took out one angle and two angle out of the strength of our electric field. So inherently, it's just going to be constant. That's really good, but still, let's think about each individual place where we're going to have a field line going through. Let's zoom in to a particular point of our surface, and we have that coming through. That is the vector for our flux, but it's also some linear multiple of our normal vector, which is fancy words of saying if we scale our normal vector by some value, we'll get our flux vector. If we scale our flux vector by some value, we'll get our normal vector. So, well, what's the angle between two parallel vectors? It's 0. And if you recall the formula for the dot product in terms of angle magnitudes, we will get that is A, B, cosine theta, and well, cosine of 0 is 1. So this is 1. And if we're talking about the force, because, well, the electric field, my God, then what we're going to do is put in Coulomb's law right here. Coulomb's law minus the charge. So we get Q equal to 4 pi radius squared. And then it would be times the unit radius vector. However, the magnitude of the unit radius vector is 1, and we're scaling it by that, so we're just going to get this out in the end, and the vector's gone. And then in here, we have the unit normal, which, fortunately, the unit normal vector is 1 as well. So this is 1, 1, and 1. We know that this is the strength of our electric field everywhere. So, well, because of this, our statement now just becomes squared. And as we did acknowledge earlier, our radius is constant and it has no relationship with our surface. So because it is not a variable that we are integrating across, we pull it out. And so ultimately this leads us, oops, already did the wrong thing, y'all. leave us q 4 pi epsilon naught radius squared. Radius squared. What leaves us with that? Well, what is the surface area of a sphere? Surface area of a sphere is 4 pi r squared. So let's go ahead, write out what we have again. Squared. And that is inherently also just 4 pi r squared. I think it's pretty obvious what happens here. For once, we get to use the red chalk. That comes out. That comes out. That comes out. That leaves us with q over epsilon naught. And so there is the argument behind Gauss's law. However, one thing that has to be made very obvious is that this is assuming it for a sphere. We proved Gauss's law for a sphere and not the general enclosed case. It gets a lot more complicated. In fact, I don't think it's anything that I'm able to do at the moment, so I'm not going to pretend to be able to do the generalized case for Gauss's law. However, I'll pretend to be able to know it for a sphere because I do. And that is inherently kind of way around it. You're going to have to get used to the idea of vectors and dot products at the very least to be able to work with this kind of stuff. I think that it'll never hurt you to learn more in the first place anyways. I don't think there's anything else to talk about, because that's flux. I include the divergence formula. Yeah. Well, thank you.